Hi guys, it's Mrs. Jackson. I'm going to take you through one last review over predicting products for chemical reactions. I know that this can be a little bit daunting and maybe sometimes overwhelming, but again, if you just kind of stop and take your time and determine what sort of reaction you're looking at, you can do this successfully. Many of you have already gained significant ground in your ability to predict products. And so I'm creating a video just as a review over the big types of reactions that you should be able to complete for our assessment. So we will be prepared, not scared. All right, the first type I want to look at is one of the ones that I consider to be probably the easiest, and those are the double replacement. So when you are looking at a double replacement reaction, those are going to be the ones that, if you remember, they have two ionic compounds as reactants. And what they're going to do is they're just simply going to trade ions. You've got your outies are going to reconnect here, okay? And your innies are going to reconnect here. These are the ones that I call split and switch. So you can see here that on the reactant side we had sodium chloride and silver nitrate. The sodium here with a +1 charge. So Na is a +1, Cl is a -1. My silver nitrate, Ag, is a +1, and nitrate is an NO3 with a -1 charge. All they did was trade ion partners. So the sodium connected to the nitrate, which is why we have sodium nitrate, and then the silver here with the +1 connected to the chloride, which is why we have silver chloride here. So let's look at another example or two. So in this reaction, I've got aluminum chloride and I have sodium sulfate. So the first thing I want to do is split and switch. So I split the cation off the front. The cation is your metal, so I split the cation off the front. And then you need to remember that your products are going to be where we've switched our ions. All right, so what we're going to do is we're going to look at these charges for our ions in our reactants. So when I look at my aluminum chloride, I have an aluminum ion with a 3+ charge, and then I have chloride ions that each have a -1 charge. Notice that I didn't bring my 3 down. I'm just interested in this ion and its charge of -1. Then I come over to the sodium sulfate. So this is sodium sulfate, and again, you break the cation off of the front. So I have sodium ions with a +1 charge, and you've got sulfate is SO4, and it's one polyatomic ion. That's on your ion sheet that's on the back of your periodic table. So what I do is I'm going to connect my outies, crisscross and reduce, and I'm going to connect my inners, those ions on the inside, crisscross, reduce. So when I mark, okay, aluminum is going to go with sulfate. Okay, so I have aluminum with a 3+ charge, and I have sulfate, SO4, that has a 2- charge. And I'm going to crisscross those values down just like we have been, and my product will be Al2, parentheses, SO43. And then I have to figure out the remaining product, and this is where I'm going to take the sodium and it's going to bond with the chloride. Now these are each a +1 or a +1 and a -1, but you have to list the positive ion first. So that cation goes in the front and you wind up with NaCl. So your final products are aluminum sulfate, Al2SO43, and sodium chloride. Okay, for the bottom, we're going to do much the same thing, right? I'm going to split my ions apart. So on the left-hand side, I have magnesium ions with a 2+ charge. I have hydroxides with a -1 charge. For the sulfuric acid, I have hydrogen ions with a +1 charge, and we have our sulfate ion with a 2- charge. So again, okay, we're going to connect the outsides together and we're going to connect the insides together. So when I work for my products, I'm going to connect magnesium with a 2+ charge and sulfate with a 2- charge. When I crisscross reduce, okay, I bring a 2 outside each of these, and I wind up with Mg2SO4 with 2 outside. And because I have 2 of the sulfates here, and I have 2 of the magnesium here, those will reduce. So my final answer for the formula will be MgSO4. Then I write the formula for my other product by connecting my 2 inside ions. I have a +1 and a -1, so I wind up with HOH. You can leave it as HOH if you want to, or you can write it as we normally might at H2O. And that's how you do those double replacement. Those are split and switch, crisscross and reduce. The next type that we need to look at are single replacement reactions. There's 2 kinds: metal replacement, which are sometimes called cation replacement. Okay, so your metals are always going to be positively charged, which is what a cation is. They look a little bit like this. You have a lone element, zinc, all right, and when you look at that lone element, if it is a metal, then you have a metal replacement reaction, all right? Okay. When I look at my element, the zinc, all right, and I recognize that I have a single replacement reaction, I then have to check my activity series of metals. The rule for single replacement reactions is the most reactive element goes to compound, the least reactive element winds up alone. So over here, I've got zinc listed right here, and hydrogen is listed way down here. So hydrogen is the least reactive, so he winds up alone. So he is written by himself right here. And then you have the zinc goes into compound, and you have zinc sulfide. The zinc sulfide formula is ZNS because you've looked up charges and crisscross reduced. So let's look at an example. So for this one, I know that I have single replacement because I have a single element and I have an ionic compound. So this is going to be single replacement. The next thing I have to do is I have to check the reactivities. Here's my silver way down here, and copper is just right above it. The least reactive element winds up alone. So since silver is the least reactive element and he's already alone, I don't actually have to do anything to this problem. The least reactive element is already alone, so on this particular example, no reaction takes place. Coming down to the next example, I've got iron as my single element. Okay, if I have a single element and a compound, I know this is going to be a single replacement reaction. When I find iron, it's located here on my list, and copper is located down below. The least reactive element winds up alone, so copper is going to wind up all by himself. So copper gets written as Cu. I don't bring any subscript with it, it's just copper by itself. The other compound then is going to be with iron and chloride. Now in this case, there's no charge given for which iron to use. You have 2 choices. You can choose either that you like. Iron I'm going to use has a 2+ charge, and I know it's going to bond with chloride with a -1 charge. When I crisscross reduce, I wind up with FeCl2. If you were to choose iron with a 3 charge, you would wind up with something very similar. If you have iron with an Fe3+ and Cl-, your final formula could have been, your final formula would have been FeCl3 if you had chosen the other iron ion. On an assessment, you would be instructed which of the ion charges to use. The other type of single replacement reaction involves halogens, and these are also called anion replacements. Okay, These are called anion replacements sometimes, and they work in exactly the same way. But when I identify my single element as a halogen, you have to understand it's going to replace the other halogen. The least reactive element still winds up alone, and for halogens, their reactivity is exactly how they are ordered on the periodic table. So when I'm looking over here at my halogens, fluorine is the most reactive and iodine is at the bottom. So when I look at this sample equation here, iodine reacting with calcium bromide, iodine cannot replace bromine because iodine is the least reactive. So this is another example of one that would be no reaction because the least reactive element is already on its own. So this reaction will not occur. So let's look at one that will. So on this page, okay, we're looking at chlorine as my lone element. So when I recognize I have a single replacement, I need to look at the single element or the lone element to decide if it's anion or halogen. Well, this is a halogen, so I know that it's going to replace the other halogen. So I have to compare over here on the right my chlorine and the bromine. The least reactive winds up alone. Okay? Bromine is lower than chlorine, so it ends up alone. So I have to put on my bromine. I then have to check Brinkelhoff, your diatomic elements. Bromine is 1, so it gets a 2. Bromine is a part of Brinkelhoff. Then I have to write the formula for the product. I've got potassium with a +1 charge, and I've got chlorine with a -1 charge. Remember that we don't use the subscripts we don't use the subscripts for the Brinkelhoff unless they are alone. Chlorine is not going to be alone. Chlorine is going to be with potassium. I have a +1 and a -1. So when I crisscross reduce, I have KCl. On the bottom reaction, I've got chlorine again as my single element. When I check and compare that to the iodine, chlorine is up here, iodine is down here. Iodine is the least reactive, so iodine winds up alone. I write my symbol and then check Brinkelhoff. Because iodine is a part of Brinkelhoff, he gets the 2. Now I need to fill in my formula for the ionic compound. Sodium is a +1, chloride will be a -1. So I have +1, -1 when I crisscross reduce NaCl as my final product answer. Okay. All right. Combustion are pretty easy. There's actually 2 types of combustion. There's complete combustion and incomplete combustion. For our class, we're just looking at complete combustion. So this is all you will be held responsible for. This is going to be where you have oxygen reacting with a hydrocarbon. So down here in the green, here's my general formula for a hydrocarbon. It always has to have hydrogen and carbon, kind of a duh moment there. It can have oxygen in this compound like a sugar might, but you have a hydrocarbon reacting with oxygen. For complete combustion, the products will always be CO2 and H2O. So here's a specific example in blue. This is actually glucose. You would have seen this in your freshman biology class. Glucose is a type of hydrocarbon of sorts, and it reacts with oxygen. I don't have to figure out the products, but I have to memorize that they are CO2 and H2O. This is what happens when you have sufficient oxygen for the reaction to go to completion, as the name indicates. There's another type called incomplete combustion where you don't get carbon dioxide, you get carbon monoxide, but we won't be working with those this year. Okay. The next to look at are the simple synthesis reactions. Simple synthesis is just going to be where we have 2 or more simple substances, like elements, coming together to make a single product. So in this example, I've got the element magnesium and the element nitrogen coming together, and you can see that I have only one product. Okay, so simple synthesis is when we're just going to have elements coming together to form what's called a binary compound. So two elements, okay, in the compound, binary, prefix bi means two, bicycle has two wheels. Okay, so let's look at an example. So in this example, I've got zinc and I have sulfur. So I know that this has to be a simple synthesis. So I look up my charges for these two elements. I find that zinc has a 2+ charge, and I find that sulfur has a 2- charge. So when I crisscross reduce, I wind up with ZnS as my final compound formula. Same process with the bottom reaction. I have sodium and I have iodine. Okay, two elements are going to come together to form a single compound. So metal, nonmetal, I look up my charges. Sodium is a +1. Iodine is a -1. Now remember, I don't bring the 2 over, just iodide. Crisscross reduce, I would have NaI. Normally, we would then go back and balance the equation. We'd need a 2 here and a 2 here to make it balanced. But that's all we do to balance those synthesis, those simple synthesis. For the complex synthesis, these are going to be reactions that have at least one compound reacting with another, but you're still only going to get one product, right? So this is still the key. Only one product is going to form. So when I look at it, I've got these two compounds. I've got iron 3 oxide here first, and I've got water listed second. So when I look at this particular example, at first, you might think it's double replacement because it looks like you should be able to split and switch, but you can't split and switch because you'd be trading oxygens. This is going to be one of those complex synthesis. These will appear on the assessment only as a bonus question, okay, maybe an extra credit question, but you should be able to check your cheat sheet and figure out the answer. So let's look at how that works. So when I look at my cheat sheet, I'm going to go back and forth. So when I look at my cheat sheet, I've got iron oxide. So iron is a metal. So this is an example of a metal oxide. And then this is obviously water. So when I look at my cheat sheet, I go down and I start looking at my examples. The first one is the metal plus the nonmetal, the binary salt. This was what we looked at as a simple synthesis. So it's not number 1. Okay, and this number 2 says it's a nonmetal oxide, and that's not what I have. We established that we're working with a metal oxide and water. So I start by going down and looking at number 3. Number 3 has a metal oxide and water. Well, lo and behold, that matches what we're working with, and it tells me I should have a metal hydroxide as the answer. So I come back and I look, a metal hydroxide is the answer. So when you have the metal oxide and water, you get the metal hydroxide as a product. You would look at your formula with the metal. Okay. The formula with the metal tells me that I have iron. If I uncrisscross, I see that it's an iron 3. And then my cheat sheet told me it was hydroxide. And so I would have the hydroxide ion. And then I would crisscross reduce. And that's where the formula FeOH3 has come from. So let's look at another example. In the example here at the bottom, I've got lithium oxide and I have carbon dioxide. So again, I am working with a metal oxide. So I go to my cheat sheet and I start comparing. I know that it isn't a metal nonmetal combination. I know that it's not a nonmetal oxide. Number 3 says a metal oxide, but it says water, and I have carbon dioxide. So I know it isn't number 3. So we've eliminated number 1, number 2, number 3. So we're going to keep coming down to the bottom. Okay. Number 4 says a metal chloride. Well, that's not what I have, so I'm going to eliminate 4. Number 5 says a nonmetal oxide and a metal oxide, so that could be a possibility, but I'm going to look to see if there's anything more specific. I get down to number 6, and it says a metal oxide with carbon dioxide, which is exactly what we have, metal oxide and carbon dioxide. So I know that rule number 6 is what I'm going to look at. And it tells me that I have a metal carbonate. So I have to find my metal, which is lithium. Lithium is Li with a +1 charge. And then I look up carbonate on my ion chart. On my ion chart, carbonate is a CO3 ion with a 2- charge. When I crisscross reduce, my final formula is going to be Li2CO3, and that's my metal carbonate for this answer. Again, those you can use your cheat sheet to solve, and you will have that available to you on your quiz. Decomposition is very similar. Decomposition reactions are just the reverse of synthesis. This is when I have a single reactant, which is going to be a compound, breaks down into its elements. For simple decomposition, we're only going to wind up with elements. So for this first example, we've got water breaking down into hydrogen and oxygen. As before, we're looking at these Brinkelhoff diatomic elements. Because hydrogen is one of the Brinkelhoff 7, he gets a 2. Because oxygen is also part of the Brinkelhoff 7, he gets a 2. That only applies when the elements are by themselves. So let's work at an example below. So now I've got iron 3 bromide, and it's going to break apart. So I know that I'm going to get my 2 elements, so I'm going to write iron. And then I check my Brinkelhoff 7. Because iron is not present in this list, he does not get a subscript. We leave him as he is. And then I get bromine. I don't just bring over this 3 that's attached to bromine on the left. Okay? When elements are by themselves, okay, you do not drag the previous exponent or subscript with you. But I do come to this side, and I see that bromine here is also in the list of Brinkelhoff. So I know that bromine by himself has to have the 2. Okay. In order to balance it, you would go back in and you would add a 3 in front here. You would add a 2 in front here. You would give a 2 to the iron, and you would put a 3 in front of bromine. For the complex decomposition, we're looking at the reverse of the complex synthesis. This is where you have a compound that has 3 or more elements. They're going to break down into smaller compounds. So with this example, I've got a metal, and then I've got CO3. And CO3 is carbonate. So I come down to my list. It's not a salt. It's not an acid. It's not a hydroxide. It doesn't have any chlorine, so it's not a metal chlorate. I am looking at number 6, a metal carbonate breaking down. So this is my metal carbonate, and it's going to break down into a metal oxide, which is what we have here, and a molecule of carbon dioxide, which is what we have located here. So if we work another example, I look at my compound, I have a metal, and then I've got this CO3 ion. Well, if you look at your chart and you look for ClO3 with a -1 charge is chlorate. So what we're working with is number 4, a metal chlorate. And it's going to break down into a metal chloride and oxygen. Well, I'm going to go ahead and write the oxygen because that's the easiest one to write. Oxygen is part of Brinkelhoff, so I give it a 2. And then I have to figure out the other formula, the metal chloride that's going to go into my blank. Well, my metal is iron. Okay, so I know it's iron, and I uncrisscross to figure out that I'm working with iron 3. So I'm going to have iron with a 3 charge, and it says chloride. Chloride, when you look it up, is a -1. When I crisscross reduce, I have Fe, Cl, and 3. So I hope these examples have been helpful for you. If you are still struggling, don't hesitate to reach out. via email and let me know. Otherwise, use these as a starting place for your review. You can use these as you begin to practice some of the other problems you've already seen. And again, let me know if you've got any questions. Bye.